All right, so picking up where the previous video had left off, we're going to start looking at atoms. We talked about it a little bit, but these are just going to be essentially the building blocks of matter is one common term used for them. But these are going to be the smallest particle of an element. So if we look here, this is just going to be two different pictures of gold. So we've just got a regular gold sample, something that you could handle on the left in image A. Oops, I don't want that. So here we've just got a relatively actually without knowing the actual scale, but I don't know the size. But with this sample, there's going to be a crazy amount of atoms actually present. So whatever you would guess for this number, I can guarantee it's almost certainly going to be an even larger number, something on the scale of something times 10 to the 20 something as the exponent. So if you think about the number, it's going to be like 5 and then 20 something zeros afterwards, because these atoms are going to be extremely small. Later on, we'll learn that the difference between different elements is going to be based on what those atoms are actually made of. So there's even smaller particles, subatomic particles, called protons, neutrons, and electrons. But the atom itself is just going to be the smallest particle for those elements. And then on the right here, you can see a scanning tunneling microscope. So this is going to be a very high-powered microscope. And we can see in this case, each of these little circles is actually representing a single gold atom. But these microscopes are much higher power than a traditional microscope that you might use in like a biology class to examine maybe like a cell or something like that, because these atoms are going to be much, much tinier. But with these atoms, we can't simplify these any further. So if you think about this sample here, we could maybe physically, if we had an extremely sharp knife, we could maybe go through and cut out these individual gold atoms. But because this is the simplest form of matter, basically, once we were able to isolate one of those gold atoms, we wouldn't be able to cut it any further. Different reactions we'll see have the movement of electrons, nuclear reactions, which are a whole big thing that we'll cover in third quarter, excuse me. Can have things occur where we change the element, but if we're thinking about general processes, once we get down to that individual atom, we can't simplify it any further. But we can take those atoms, and like it says here, have them enter chemical combinations. So we can have them take part in reactions and then join with other substances to form other compounds that we're going to refer to as compounds. So with it, we've got molecules here. And what I'm going to do for a second is actually skip ahead to this next slide, just because I think the image itself helps solidify the information a little bit better. But on the left here, we've got elements. And this is just looking at one single element. So you can see here we've got a circle, and it's kind of like a Venn diagram with multiple pieces here. But this element circle, you can see all of these examples, even though we've got 2 oxygens or 2 hydrogens with these ones, all of these examples are just that single element by itself. So even if we've got it in combination with multiple of that element, it's still just referred to as an element. So diatomic oxygen, the oxygen we breathe, is 2 oxygen atoms combined. Hydrogen exists similarly, and we'll see there's a group on the periodic table where they're all diatomic like this. Nitrogen is the largest component of the atmosphere, is diatomic like this, so it would be 2 nitrogen atoms bonded together. Or it can just be the individual elements here, like we see with lithium or potassium or sodium. But once we take individual atoms and combine them in 2 or more, that's where we see molecules. So looking at this big circle here, oh, and I didn't realize that this image had the mouse right there. But looking at this big circle here, we can see molecules. And now this includes oxygen, hydrogen, as well as these examples, because a molecule is just going to be a combination of 2 or more atoms. And it doesn't matter if those atoms are different or not. So these 2, oxygen and hydrogen, same elements, 2 oxygen, 2 hydrogen. Whereas these ones, we've got nitrogen with oxygen, water, so we've got hydrogen and oxygen. That's a typo, should be CH4 for methane, carbon and hydrogen, carbon dioxide, CO2. So we've got those combinations, But in each case, we've got multiple atoms bonded together. So that's where we're looking at molecules, a combination of atoms. But within this molecule circle, we've got an even smaller one known as compound. And then notice there's no overlap between element and compound. So a molecule could be an element, a molecule could be a compound, but an element and a compound will never be the same thing, because in this case, with the compounds, we're taking, in this case, it's only 2 elements for each, but we could have 3 elements, we could have 4 different ones, but we're taking different elements and combining them together. So nitrogen and oxygen again, hydrogen, oxygen, and so forth. So when we're looking at these, a molecule is a combination of 2 or more atoms, doesn't matter what they are, but a compound is a combination of 2 or more atoms that have to be different. And one way you can think about this is sort of like all thumbs are fingers, but not all fingers are thumbs. It's the same thing here. All compounds are molecules, because you can see all 4 of these examples completely fit in this molecule circle as well, but not all molecules are compounds, because we've also got oxygen and hydrogen here. So I'll just go back to that previous slide for a second. And the reason we're discussing this is, for the most part, there's very few elements that actually do exist as those individual atoms in nature. Even going forward again, potassium, lithium, and sodium, we're going to learn are extremely reactive. So you would never actually find just a single sodium atom sort of hanging out by itself in nature. And the same thing with lithium or potassium, Li and K. For the most part, if you look at a periodic table, the stuff all the way to the right, so that final column going up and down all the way on the right-hand side, those elements exist as individual atoms, but for the most part, we've got everything else in either a molecule or specifically a compound if they're with something different. But again, we just want to make sure that those terms, we know what they represent, because they're similar, molecule and compound, but there is a distinction between those two. And again, all compounds are molecules, but not all molecules are compounds. And that's why here we've got all the atoms are the same, different types of atoms, both represent molecules, but this bottom definition only applies to compounds here. And again, with these examples, they kept it relatively simple with this image. In each of those compounds, we only had a collection of 2 different elements, but we could have a whole bunch of different stuff. So baking soda, for instance, is going to be a combination of sodium, hydrogen, carbon, and then oxygen. Biological compounds can have a whole bunch of different elements in there, so it doesn't just have to be 2. It just has to be 2 or more. And you can see here glucose, C6H12O6. So we've got 3 different elements there. That's going to be a relatively, at least compared to the ones we've seen so far, a relatively large molecule that we can also classify as a compound, since we do have those different types of atoms. Carbon dioxide, the production of, or the byproduct of the combustion of fossil fuels, is going to be a compound. Water, also a product of combustion, going to be a compound. Whereas these ones all represent molecules, but from hydrogen, oxygen, phosphorus, and sulfur only represent molecules in the sense of molecule and compound. They can also be considered elements, since it's just either sulfur or just phosphorus or just oxygen, just hydrogen. But you can kind of draw a line up and down the middle here. I think I can actually do that here, between element and compound. So all of these are molecules because all of them have a collection of atoms, but to the left of that line, it's just the same type of atom with one another, so only sulfur. So all of these are going to be elements, while the ones to the right would be considered compounds, because we've got different elements with one another. And then when we're looking at matter, because that's everything we've been describing so far, kind of falls under that umbrella, there's going to be different ways we can describe it in terms of the properties. And one sort of classification of those properties is going to be physical properties. And with these properties, we're thinking about things that can be observed or be measured without changing the identity of that substance. So we can kind of think of these as aesthetic properties, because they show us, or they typically apply to like the appearance of that substance, but it doesn't actually get towards the identity of it. So if you think about color, you could paint the wall of whatever room you're in, still going to be a wall. So we haven't changed what that is, we just changed what it looks like. Same thing with like things like mass and length. We can take a sample and cut it in half or pour half of it out. And now we've got a smaller sample, but it's still that same sample. So we haven't changed what the identity of that substance is. Whereas with chemical properties, in order to observe these properties, the composition of that sample, of that substance, must be changed by a chemical process, or otherwise known as a chemical reaction. So just looking at a few of these, some of these, depending on what chemistry you've taken in the past, may be familiar to you or not. So oxidation state we'll talk about later in the course. Heat of combustion is essentially just how much energy is released when you burn something. Coordination number, we kind of touch on a little bit in one of the later chapters. But if we think about just something like flammability, essentially just will something burn or not? In order to observe that, we actually need to burn something. And then in that process, it's getting combined with oxygen. So we're creating an entirely new substance. So if you think about a candle, for instance, if you've ever put the lid back on a candle, the candle itself goes out pretty quickly, because by putting the lid on, you're cutting off the supply of oxygen. And that burning process is just taking whatever that substance is that we're burning and essentially just combining it with oxygen to form something new. And it's not 100% of the case. Actually, I'll save that. That doesn't really apply here as much as with the chemical changes. But same thing with reactivity. If we want to see how reactive something is, we actually need to have it take place in a reaction. And in that case, by definition, we're creating something new. So we're going to change the identity of that substance. And a lot of these are similar. Toxicity, oftentimes when you're exposed to a toxic substance, your body actually metabolizes it into something else. And that's what winds up doing the damage, that new metabolized product. So we're, again, changing it into something new. And then with some of the other ones here that might be a little bit more abstract to you, like I said, we'll talk about a lot of these at different points throughout the Gen Chem series. Okay. So with this, just thinking about what we talked about on the previous couple of slides, we've got a paragraph here that has different properties underlined. And what I want you to do is just pause, take a minute to kind of read through this, look at those different underlying pieces, and then see if you can identify which of them represent a chemical property, which of them represent a physical property. And then on the next slide, I just got it color coded, so I'll highlight the physical in yellow, the chemical properties in green, just so you can see those. But I'd recommend just pausing the video, taking a minute to kind of give yourself that chance to practice. But just to read through it quick, classify the 6 underlined properties in the following paragraph as chemical or physical. Fluorine is a pale yellow gas that reacts with most substances. The free element melts at negative 220 degrees Celsius and boils at negative 188 degrees Celsius. Finely divided metals burn in fluorine with a bright flame. 19 grams of fluorine will react with 1 gram of hydrogen. Okay. And then if you still want a chance to practice on your own, like I said, just pause the video. Otherwise, I'm just going to kind of continue. But with these different underlying pieces, we want to think about, does that represent a change in its appearance, or does that represent a change in its identity in order to determine if it's physical or chemical? But looking at the first one, fluorine is a pale yellow gas. So since we're just underlining gas, that's going to be a physical property, because that's just describing the state of matter, but it's not describing what that substance is. It's not describing the identity. We could have fluorine as a liquid. We could have fluorine as a solid, would still be fluorine. So just knowing it's a gas is only going to be a physical property. But now that we have reacts with most substances, that's going to be a chemical property because within that process of reacting, we're going to be changing it into something completely new. And then with the next one, melts at negative 220 degrees Celsius. So this one, and the same thing with boils at 100 or negative 188 degrees Celsius. Those might be a little bit tricky because a lot of the times when people see those phase changes, so melting or boiling something, they think that's going to be a chemical change. But what we're doing there is, again, just only affecting the state of matter. But as we melt or boil something, it still stays that same substance. It just changes from liquid to gas or gas to solid or solid to liquid, whatever it may be, depending on that particular phase change. So in this case, melts at negative 220 degrees Celsius. Going solid to liquid is just going to be a physical property. The process of melting, of actually melting would be a physical change, but the temperature at which that occurs is just a physical property. And the same thing with boils at negative 188 degrees C. Since we're focused on the temperature there, that's why we're describing a physical property. If we were focused on the process of boiling it though, then that would be a physical change. And then with the next one, burns in fluorine. So just like I mentioned, flammability. Typically we think about it in the sense of burning in the presence of oxygen. But we can also burn things like we see here in the presence of fluorine. So that would be a chemical change. Just because throughout that process, we're going to have the metal and the fluorine combined to create a new substance. And then with the last one, this one's a little bit tricky. I think if we were to read it as a whole, we would probably wind up with a chemical change just because we have react in there, or chemical property, excuse me, because we have it reacting. So we're going to wind up with a new substance when we have fluorine and hydrogen combined. But with this one, I've actually broke it down into different pieces because we've actually got kind of physical properties hidden in there a little bit. The 19 grams or the 1 gram of hydrogen, those are representing physical properties. How much of that substance do we have? We could then get rid of some of that 19 grams of fluorine. We would still have fluorine, we would just have less of it. We could get more hydrogen and we'd have extra of it, but we would still just have hydrogen. So in those cases, the masses would be describing physical properties, but the reaction piece is describing a chemical one. So if we could only give one answer for this, I would say it would likely be a chemical property, just because that reaction piece seems to be the most important. But the masses of those are reflecting physical properties. If we just focused on those individually. So I took this from the textbook. And with that last one, I think it's just a little bit ambiguous. Again, I think if we focus on it all at once, fit chemical property, but we can kind of isolate out those masses as physical. And then in addition to chemical versus physical, we've also got intensive and extensive properties. So the way that I remember this is if you look at intensive, IN, intensive are independent of amount. So again, IN at the beginning, meaning that these intensive properties, it doesn't matter how much of that substance we have. All that matters is what that substance is. Whereas the extensive properties are dependent on the amount of that quantity. So if we think back to the previous one, 19 grams of fluorine, 1 gram of hydrogen, those would be examples of the extensive property of mass. Because obviously if we had more or less of those samples, the mass is going to change. Same thing with volume. It's going to take up more or less space as we get more or less of it. Length, kind of a similar idea. Energy, a little bit more abstract. But as we have more and more energy, or we have a larger energy source, I guess if you want to think about it that way, we have more energy. And then enthalpy and entropy are kind of that same idea. With the intensive ones, what I want to point out is the melting and boiling points. So you probably heard in some of your science classes in the past, pure water boils at 100 degrees Celsius at sea level. And with that saying, boils at 100 degrees Celsius, I didn't have to specify how much of that substance we have. So whether it's a water bottle's worth, whether it's a swimming pool's worth, as long as both of those samples are water, the boiling point is going to be 100 degrees Celsius. What's going to be different, though, is the amount of energy, the amount of heat it takes to actually reach that boiling point. Because in the case of the swimming pool, we're going to have a much larger mass, so it's going to take a lot more energy to boil it. But the temperature itself is still just going to be 100 degrees C. And with it, you can see just a few more examples here. Some of them are the same as on the previous one. But looking at it, and again, intensive is independent of amount. So we can see the ones on the top here don't matter how much of that substance you have, it just matters what it is. So what I want to do is think about density, which is equal to taking the mass of a sample and dividing it by the volume. So how much mass does it have divided by how much space does it take up? And if we look at the extensive properties, we can see mass and volume here. Both of those are extensive. So what do you think that means in terms of density itself? Is density also going to be extensive, or is density considered intensive? Which would we put it up on top with intensive or down on the bottom with extensive? So just take a moment to try to kind of think through that one. Oops. And if you're still thinking through, again, just kind of pause the video. But what we're going to see is density is actually an intensive property. So even though mass and volume are extensive, density itself is going to be intensive. And if we think about just a simple example with a glass of water, if you have a glass of water that's half filled, you fill it up the rest of the way. We've doubled the mass now of that water, but now we're also taking up twice as much space. We're filling the entire glass now. So because the mass and the volume of a substance are going to be directly related, they're going to change at the same rate. Same thing if we cut those in half. Now we've got half as much mass, but it's taking up half as much space. So they're going to change at the same rate. So that's why density is going to be an intensive property. And that's why density can actually, in some cases, be used to help identify what a substance is, because it doesn't matter how much or how little of a substance we have. It just matters what that substance is. I was going to say something and it completely slipped my mind. Oh, and that's why when we think about water, again, I like to use water as an example just because everybody's familiar with water. It's found all over the place. And it's got some unique properties. But the density of water is roughly 1 gram per milliliter. So if we had 1 milliliter of water, we would have 1 gram, and vice versa. And with that, you don't have to specify the overall sample when we say that. So the density of water is 1 gram per milliliter. Doesn't matter if we have a water bottle's worth, if we have a swimming pool's worth, that density isn't going to change with the amount, because as we scale it up or down, the mass and the volume change accordingly. All right, and with this, we talked about physical and chemical properties. Now we're going to start looking at changes. So just as a little sort of pre-quiz on your own before we dive into it too much, see if you can just look at these examples, and some of it we already talked about, but see if you can look at these examples and determine if they're going to be physical or chemical changes. And as always, just pause the video to give yourself time. I like to just kind of keep moving so that the video itself doesn't just have a blank screen with silence for long stretches of time. But just so you have time to work through it on your own, see how you're doing, and then check your answers, just pause the video till you kind of read through those different examples. Because when we're looking at the first one, condensation of steam, like we were just mentioning before, all of the phase changes are just going to be physical. So when we're looking at these, condensation of steam, melting of gold, so A and E for the 27th one, ice melting for number 28 below it. All three of those are going to be examples of physical changes, just because they're phase changes where we're only changing what that state of matter is, but not actually what that substance is. So it's still, with the case of steam, it was H2O to start, H2O at the end. It just went from a gas to a liquid, or melting gold went from a solid to a liquid, ice melting, same idea. And then with number 27, B and C are both going to be chemical changes because those are actually creating new substances. We're changing the identity of what that substance is. So again, burning gasoline, we're going to have gasoline combine with oxygen to create carbon dioxide and water. Souring of milk, I don't know exactly what the products would be, but we're going to have the components of milk get changed into something else, and that's why you start to get that awful smell. It starts to get kind of chunky if you leave it in there long enough, because we're going to be creating new substances. Number D is often one of the more tricky ones because dissolving sugar in water, you kind of see the sugar disappear. It seems like a chemical change, but what's actually happening there is just a physical change. And one way you can think about that is we can physically separate out the sugar and water. So if we had sugar water, we could then just boil off the water, be left with sugar in that container. And if we set up an apparatus to collect it, we could then collect the boiled off water and just have those two components separate with one another. So that's going to be a physical change anytime those components can be physically separated. Whereas the burning of gasoline, not only we're creating a new substance, but in order to undo that one, basically, it would have to be another chemical change. And really, you can't unburn gasoline. Certain chemical changes we'll see can be reversed, but the physical ones are reversible via physical processes, of course. And then just with the rest of them on number 28, I already talked about ice melting as just a phase change. Coal burning is the same as gasoline burning, going to be combining that substance with oxygen to create new products, carbon dioxide and water primarily. Mixing chocolate syrup with milk. I would consider this to be a physical change. If you've ever done that, a lot of the times you just wind up with some of the chocolate syrup kind of settling at the bottom. So you've got to keep stirring it together. But when we mix those together, we're not creating a new substance. You can call it chocolate milk, but if we think about it, chocolate syrup with milk, chocolate milk, pretty much the same thing because we don't have a chemical reaction taking place there. Explosion of a firework would be chemical though, just because we're going to have that large amount of heat, we're going to have a reaction taking place, so we're going to be creating something new. And then magnetizing a screwdriver, think about it, it's still going to be a screwdriver, just now going to be magnetic. So that's just going to be an example of a physical change. So when we're trying to identify these changes, just think about if this process is changing the appearance of something, or if it's changing the identity of it. If it's the appearance, it'll be physical. If it's the identity, it'll be chemical. And you can see a few more examples here. Like I mentioned, the phase changes are always physical. In these two cases, shredding and chopping, we're just taking those pieces and making them smaller, but they're still either going to be pieces of paper in the case of shredding or firewood in the case of chopping. So the identity hasn't changed. Whereas with combustion and rusting, in both cases, we're actually taking whatever that initial substance is and combining it with oxygen. Obviously, combustion, a much more sort of violent process, whereas rusting is going to be a slower, more gradual one. But in each case, we're forming iron oxide for rusting. We're forming, depending on what the product is, we're going to have, in this case, like the carbon from the wood combining with the oxygen from the atmosphere. And then digestion and rotting, similar processes in the sense that food's being broken down into something new. In the case of the pear, you can see those brown spots. So that's occurring just on its own. But we're taking whatever the substance is initially and changing it into something new. And then with digestion, the same exact thing. So you've got enzymes in your saliva that help break down that food, stomach acid to help digest it as well, because we're taking those, the food itself and reacting in order to get different substances that the body can then better utilize. But again, the big thing, chemical change forms new products, physical change only affects the appearance essentially. And like I said, the phase changes tend to be the one that trip people up the most. But if you just think about boiling water, for instance, you're making pasta, you put the water in the pot, throw it on the stove, start heating it up. And you can see here, I like this example just because they have the lid on there. I typically, when I boil it, just have it open so you can see the steam coming off. But in this case, it really highlights the fact that this is going to be a physical change, because we have liquid water to start. We heat it up, we start getting that steam produced. But now that we have this lid here, some of that steam is going to condense on the lid, and we can still see we have that liquid water again, which really just reinforces the fact that going from liquid to gas or any other type of phase change is just going to be a physical change. Because we started with liquid water, heated it up to water vapor, but then when it condensed on the glass again, now we just have liquid water once more. And then similarly here, it's just showing wax melting. So we're starting with solid wax, heating it up. Looks like you can kind of see the initial piece started here, and then as it starts to melt, you can see it spreads out more. But again, it's just going from solid to liquid. We're not changing what that substance is at all. So this is still going to be a physical change. And with it, we'll just stop there for now, and then with the rest of the chapter, we'll be diving into measurements in units, so just in general, and then we'll look at some specific units. We'll look at how we make certain measurements, because the number of digits that we report is going to be important, and then that'll tie in with how we do certain calculations, because how we round our answers in science is going to be important, so that we're relaying the correct information, and then ultimately how we can convert between different units.